Greetings. We are continuing with our thermodynamic lectures. Today we want to look at one-dimensional steady flow. One-dimensional steady flow. If you recall from our earlier lectures, when we derived expressions for steady flow, equations for energy, we had combined, we started from first law of thermodynamics, which normally is du is equals to dq plus dw. Of course, U is internal energy, Q is heat and work, and we know what state functions are and path functions are. And from this particular equation here, remember, we derived the steady flow energy equation which was the change in enthalpy and the change involving kinetic energy, the change involving potential energy, and we say that was the same as dq minus w. That's the heat and work transfers across the walls of that open system. And this expression here was for kinetic energy. This expression here is for potential energy. And of course that is to do with enthalpy. So remember, if we assume that the elevation is not significant, then we can assume that the potential energy is zero. And so that equation reduces to dH plus dc squared over 2, that's dq minus dw. So that's first law. And we also remember that from second law of thermodynamics, we have the Clausius inequality. We have the Clausius inequality where ds greater or equal to dq over t. So it therefore follows that when we are talking of adiabatic processes, then that dq will be zero. For adiabatic processes, dq is equal to 0. Therefore, ds will basically be 0. So this was a very important expression which we derived. Now, when we consider, for example, a flow in a duct whose area, cross-sectional area varies. Let's consider asentropic flow in a duct of varying area. So, if you have asentropic flow in a duct of varying area, then the key factors which will affect the properties of that fluid, remember when we derive these particular expressions for steady state energy flow equations, we did not talk about whether there was friction involved during the flow and so forth, or the variations in cross-sectional area. And so when we are having an asentropic flow in a duct of varying area, then the key thing which will affect the fluid properties, the fluid property will be affected by the variation in the cross-sectional area, and frictional forces. Those are the two key things which will affect the fluid flow. When you are dealing with asentropic fluid flow in a duct of varying area, cross-sectional area, it will simply be the variation in the cross-sectional area which will affect the fluid properties and frictional forces. Now, when we talk of one-dimensional steady flow equation, steady flow And this is a relatively an ideal type of situation. So when we have this flow, which we call one-dimensional flow, steady flow, then there are certain conditions which will qualify that flow to fall under the category of one-dimensional flow. And one of them is that the cross-sectional area change should be gradual. The cross-sectional area change should be gradual, just like the axis of the curvature should also change gradually. Cross-sectional area change should be gradual. So there shouldn't be any abrupt change. There shouldn't be any abrupt change in the cross-sectional area. And number two, there should also be gradual change in the curvature of the axis of the duct. The curvature of the axis. So in that particular case, then we are having our one-dimensional model in terms of steady flow. So we are assuming that if it has to be a one-dimensional steady flow, then we expect that the cross-sectional area change should be gradual, and of course the change in the curvature of the axis of the duct should also be relatively gradual. And the other thing which we are assuming, which is very critical also, is that the thermodynamic and mechanical properties of that fluid, which we are calling one-dimensional steady flow, that fluid which is a one-dimensional steady flow, the thermodynamic and mechanical properties should be constant on those planes, on all the planes which are perpendicular to the axis of the duct. The thermodynamic and mechanical properties should be relatively constant. Relatively constant along planes perpendicular or normal to the axis of the duct. Those are very, very important as idealistic conditions for a one-dimensional steady flow. Very, very important for us to know that. And one of the other things which we are assuming in general, based on this assumption from Roman numeral 3, that the thermodynamic and mechanical properties are relatively constant as planes which are normal or perpendicular to the axis of the duct, then it means that the thermodynamic and mechanical properties at the inlet should be relatively constant. Just like, so the thermodynamic properties thermodynamic and mechanical properties at the inlet and outlet are relatively constant. So if you look at it, if you think of it pictorially, we are saying, think of it pictorially. Let's just draw some type of a schematic. Let's just say that you have our fluid. Let's think that this is our fluid. And we are saying that we have this plane. We have this plane. Let's just call plane 1, plane 2. And we are saying that the thermodynamic and mechanical properties along this plane here, which we are saying is perpendicular. We are saying it is perpendicular to the axis of the duct. Let us say that it is perpendicular to the axis of the duct. For this flow to be a case of a one-dimensional steady flow that is perpendicular to the duct, that means that if you have properties here, remember, we have our steady flow equation, the change in enthalpy plus the changes involving kinetic energy. We have gotten that is dq minus dw. So if you are dealing with a situation where we don't have any of work or heat involved in this transfer, because you have said if it's isentropic, then it means that there are no friction is negligible, or dq is thought of as zero, and obviously we are assuming that there will be no work. So what are we saying? We are saying that if these two quantities, work and heat, are zero, then dH is equals to dc squared over 2, where remember c is velocity. And so if you do simple integral calculus, then if you integrate both sides, let's say from some property, let's call the limits are represented by properties in plane 1 and plane 2, 1 to 2, 1 to 2, then what we have is h2 minus h1 is equals to, will be given by c2 squared over 2 minus c1 squared over 2. Therefore, what are we having here? We have this, there's a minus sign there. So that should be minus c2 squared over 2 minus c1 squared over 2. So this will be h2 plus c2 squared over 2 is equals to h1 plus c1 squared over 2. Now, what is the import of this in terms of the significance of the calculations? It means that if you know, for example, if you know the velocity at C1, at plane 1, at state point 1 represented by that plane 1, which we are saying is normal to the axis of the duct, and you also know the enthalpy 1, so if you know these properties, and you also have the value, thermodynamic value for H2, then you can compute C2. Then you can compute C2 very, very easily. You can compute C2 very, very easily. So that if you have these planes which you can assume are some infinitesimal distance apart, then you are able to compute these particular values. You're able to compute those particular values. And so in general, also, if you use the principle of conservation of mass, which is crystallized in the continuity, the equation for continuity, then you can be able to also compute the cross-sectional area. Then you can compute the cross-sectional area. How will you do that? Remember, we have said density times cross-sectional area times velocity. This is relatively constant. The continuity equation. So what are we saying? We are saying that we take cross-sectional area at state point 1 represented by the plane 1 normal to the axis of that duct, and the velocity 1, and the specific volume for 1, that should be given by the cross-sectional area at state point 2, which is given by the plane 2, which is normal to the axis of the duct at that point, and velocity 2 over v2. So basically, A C over v is a constant. So you are able, based on continuity equation, to be able to compute the cross-sectional area changes, the cross-sectional area in that flow, in that particular isentropic flow in that duct there. So if we represent this graphically, we can represent these quantities graphically. So graphical representation will lead us to this kind of pattern. So if you have the ratio of the pressure at the points corresponding to the planes, state point 2 and 1, that ratio at this point axis is 1 and here it is 0. So what are we saying? We are saying that at this particular point, P2 over P1, P2 is equals to P1, and as we move this way, then what is happening? Then the pressure is dropping. P2 is decreasing. And so if we have the specific volume, V1, specific, and we have the velocity, C1, we have area, A1, then as we progress, that is, as the pressure decreases, and remember from Boyle's law, pressure is inversely proportional to volume. So as the pressure is decreasing, then we expect the volume to be increasing. Volume to be increasing. So what are we talking about here? So we are saying that in this particular profile, we are going to see that as the velocity increases gradually, there will also be a gradual increase in the specific volume. So we note that as the velocity fluid increases gradually, so does the specific volume. But when it comes to the cross-sectional area, as these ones are increasing gradually, you will find that, V2, this is V2, C2, you will find that there is first a decrease, cross-sectional area, then an increase. There will be first a decrease. In the case of cross-sectional area, there will be a decrease first, followed by an increase. So there will be a decrease first, followed by an increase. And that pressure ratio corresponding to that minimum for the area, that pressure ratio corresponding to that minimum area corresponding to the minimum in the area is referred to as the critical pressure ratio. Critical pressure ratio. And think of it as CPR. So that corresponds to the critical pressure ratio. So you notice the specific volume will increase gradually just as the velocity increases gradually. But the area will decrease. And this decrease in area is actually, if you look at that equation which we talked about of continuity, then you will see that it does make sense because there is the specific volume increases gradually but increases steeply towards the end. And there are certain cases where you can always assume that the specific volume is constant. You can always, there are cases where for ease of calculations, you can assume the specific volume is constant, and in that particular case, you are thinking of an incompressible fluid. You can think of the specific volume as constant. That will make our calculations a lot easier, And that in that particular case, you are thinking of an incompressible fluid. So for now, let us stop at this particular point. We are continuing with these steady flow processes. We are continuing with these steady flow processes.